Hello and welcome to the second lecture of Dynamics of Solids and Fluids in Geoscience System. Last lecture we addressed a fundamental aspect of porous systems which is related to their static property, porosity. Porosity was found to be the volume fraction of interconnected pores of a porous sample. But porosity is only a static property. It doesn't tell us how fluid flow can happen inside our porous sample or through the pores of this porous sample. This lecture is about that, is about flow inside these porous samples, or the sample that we created yesterday as it was called sand pack, which has sands inside a pack system. To study flow in porous media, we have to go back to 1856, city of Dijon in France, when Henry Darcy, a hydraulic engineer, was tasked to design water purification system for the growing city of Dijon. So Darcy had a question in mind. If he creates a water filter by making sand pack like this and let the water flow through this sand pack, how would this water flow govern? What would be it depending on? How fast would the discharge flow rate will be? So he started to analyze this extremely simple but very intuitive system. Let's look at what drives the flow. Potential or pressure difference, and potential difference is the driving engine for flow to happen. So this is the bottom of the sample, let's say location B, and it has potential B. At the top of the sample, we have potential A. At the top, consider we are exposing it to atmospheric pressure, or we have a pump of water that is having a lot of pressure, for example, imposed in the system. We want to study how fluid flow happens in it. What's the potential? Potential is the thermodynamic pressure at the point plus the gravitational effect, which is the potential, also called. So density of water, if my fluid is water, which is the case, gravitational acceleration, and elevation from a reference level. Any level, doesn't matter, because the difference matters for the flow, not the absolute value. So we take the bottom of the sample as the reference for Z, which is going upward, and it starts from 0 here. So Z at location B will be 0. Potential at the top is pressure at the top, A, plus density of water, gravity, and Z at A. Imagine the sample has the size, length of L. So ZA would be L in this case. Darcy said the flow rate that happens through this system, the volumetric flow rate that has the dimension of cubic meter per second, if divided by the total cross-section area A total, the cross-section area of this sample, which is pi r square, the radius of it, that can be defined as an average velocity u, which is the velocity of nothing, is superficial velocity, so we call it Darcy velocity, for example, and that is proportional, naturally, by the difference of the potential that the point A and B have and how far they are from each other. If you make higher potential difference across the same L length, you get faster flow, naturally, because you get higher force for driving the flow. And there are now some parameters here, coefficients, that need to make the relationship hold. One aspect of this flow is that this is a flow of a fluid. How easy or how hard a fluid can flow, given the shear or the stress given to it for flow, is defined in physics of fluid as the viscosity. If you put honey to flow, or water to flow, or hydrogen to flow, they will have different viscosities. And viscosity, the higher it is, the more difficult for the fluid is to flow. So it goes to the denominator of this equation. That's the viscosity of your fluid, which is a fluid property, and it is in the unit of Pascal second. Now we are left with the remainder. What's the rock property? How rock contributes to how easy or how difficult the flow through the pores of the rock is. That coefficient is called permeability K. Permeability is the factor that quantifies how easy, how convenient flow through the pores of a rock or a porous medium is. So that's the K, and has the dimension of meter square. Permeability. This is potential difference. The potential difference has the dimension of Pascal. Length has the dimension of meter. Viscosity is Pascal second. Pascal is going to cancel. You have meter per second per meter here, and here velocity is meter per second. If you do the mathematics of this dimension, permeability is meter square. So that's the real permeability that we can measure now for a sand pack like this that we created yesterday in the first lecture. I'm not sure if you're listening to it in the day after. And if I inject, for example, water on top of this sample, I can actually make flow happen. Do you see? I hope you see the droplets going through this. And if I want faster flow, I can just blow to make it go faster because I'm increasing the pressure at the location A for this sample to go. And I can measure the volume of water flowing through a given second's time to find the flow rate and do the math to find K. In the laboratory environments for rocks, for these rocks, it's not possible to just put water here and then measure what the flow rate is. It's very, very tight. So what happens is we put the rock in a flooding system that flows through, the fluid flows through this rock by enforcement of a pump at, for example, here PA and here PB with a rock of distance L. And so when I measure the flow rate over the cross section of my rock to get the average velocity, I find that it is K over viscosity, PA minus PB divided by L. And given the pressure that I pose, I can put, for example, 100 bar, 100 atmosphere there, and then get force of the hydrogen flow or CO2 or water through the rock. Now, this is my, for example, x-axis. And if I want to do the mathematics right, I need to do the PB minus PA so that it goes to the right side of the axis. So that leads to minus K over viscosity, PB minus PA over L. And in the limit of a small l, that ends to be that U will be minus K over viscosity gradient of pressure. For 1D case, this is equal to gradient, which is dP dx. In this case of 1D, I can write it minus K over viscosity dP dx, or PB minus PA over L in this linear system. More on the multidimensionality of the pressure gradient and velocity and tensorial effect of K comes next. Right now, we are assuming K is a scalar property, is a scalar rock property. And we would like to now go a little bit further and understand how can, like porosity, remember we measured porosity directly or indirectly. Now I want to do the same practice for K. We studied how can we measure it in the laboratory, whether with the force of core flood experiments. So this is called core flooding. If you see papers and articles, core flood system is exactly this system that flows through a fluid in this rock. And that's the experimental way to find K of this rock. Now I would like to model and understand my system. By pen and paper, I'm going to show you how can we estimate the permeability of this rock. So let's get started. This is the Darcy law. I am going to now go to the next part and say how can we model this system. The porous rock, which is like this, is this rock. I put it here so you see it's exactly like this, yeah? For mathematical analysis of permeability, what we do is we do a very, very simple but extremely meaningful step of simplification. We assume that this rock consists of several tubes, several capillary tubes that form pathways for the fluid to take place. And we look into one of them. Let's look into one of them. This is one tube zoomed in for the purpose of the convenience of this course. So this tube has the diameter D or radius capital R. If I look it from this side, it has this cross section which is circular, right? It is extended in Z direction and radial coordinate is R. So it's a cylindrical coordinate system. Now, if I do Navier-Stokes momentum balance and the continuity equation, which is mass balance, and apply certain assumptions that hold for this system that Darcy studied, what are they? No slip at the wall boundary. At the wall, the velocity should be zero. Fluid sticks to the roughness of the rock. Steady state, fully developed boundary condition, boundary effect, fully developed boundary layer, and single phase flow, single phase incompressible flow. Under these assumptions, I will show in the future lectures that Navier-Stokes equation gives you the velocity across this tube. So this is a cross section, for example. The velocity profile will be given like that. This is V parallel to the Z axis. And it becomes zero when it touches the rock or the tube wall. The formula that we get from the Stokes analysis is that velocity across Z-axis will be minus capital R squared, the radius of the tube, minus R squared, the small radius of the tube, over the 4 mu gradient of pressure across Z-axis, which is Z pressure here, B minus A over L, distance. That's the VZ. Now, this is the velocity of the water, and we can check it. For example, velocity at radius is equal 0 will be minus R2 over 4 mu gradient PZ, which is the maximum velocity. Maximum velocity at r is capital R will be r square minus r square over 4 mu dp dz, which is actually 0. And that's exactly at the wall. At the wall, velocity should be 0. That's the no slip condition. Now I would like to relate it to Darcy law. So what I'm going to do is, I would like to know what's the average velocity across this tube, which is the flow rate going through divided by cross-section area. What is the flow rate? See, if I just make this cross-section tube a bit bigger for you, so this is the cross-section. From here, I go to the distance r and I make just a band, a small area, which is a ring with the thickness of dr. Velocity at that location is known to me. So to know the total flow rate, I need to integrate from r0 to r capital R, velocity at that r location times the cross-section area of this disk, which is, or band disk, which is 2 pi r dr. 2 pi r is the perimeter times the thickness, which is dr. It gives me the cross-section area. And then divided by the total cross-section area, which is pi capital R square. Now, if I plug my Vz here, velocity, as a function of r, what is it here? This is my velocity, which is a function of r. I plug it here, I obtain my velocity average is integration from 0 to capital R of minus, let's put minus out, R2 minus R2 over 4 mu. Then I have gradient Pz multiplied by 2 pi r dr. And then divided by pi r square. Now it's extremely a convenient mathematical practice to do the integration here, because it's only a function of r and its dp dz is constant, gets out, and it's very simple. You will find that the u average here will be minus r square over 8 mu dp dz. Fantastic. You have the dp dz here, and you have dp dx or dp dz there. It's Darcy's law. Viscosity is here, and in the Darcy's law too. So what would be the permeability associated with single tube? The permeability associated with single tube using bundle of tube theory is r square over 8. Fantastic. How about if my rock had only a few percent of it, or some percent of it, porous? So I had a rock sample that had these tubes, and they were not entire surface of it, because the porosity is phi and it's less than 1. Then the bundle of tube says that your K would be the volume fraction available for the flow compared to the total, because velocity of the Darcy is divided by the total cross-section area and not just the pore volume cross-section area. And in that case, the bundle of tube would say permeability is porosity r square over 8. Fantastic. Now I would like to find permeability of a sand pack like this. But these are sand packs of spherical grains. Flow through them is not like flow through a cross-section that is circular. It's very complex. So how can I extend it to non-circular diameters or geometries? Let's move on. Now, I am reaching one step towards my sandbag. My sandbag is a pack of spherical grains that form my porous system. They have the diameter of dp. Flow happens inside the channels that are here. Flow happens here. They are not straight type of cross-section areas. What cross-section area they have? They have a cross-section area like this unit cell that I'm going to plot for you. So this is a quarter of a grain. This is a quarter of the other. So like this kind of cross-section area. This is my grain, and the fluid flow happens in this yellow highlighted butterfly-shaped geometry. How can I find permeability for a butterfly-shaped geometry that is in here? Hydraulic engineers have defined a very, very neat way forward for non-circular cross-sections, and that's called hydraulic radius. Hydraulic radius, R hydraulic, is the pore volume available for flow divided by wetted surface. Wetted surface. For a circular tube, so circular tube, hydraulic radius would be pore volume available, which is pi r squared times L over wetted surface, which will be 2 pi r L, which will be r divided by half. You can also calculate hydraulic radius, by the way, in some fluid mechanics textbooks as the wetted cross-section area over perimeter, wet perimeter. In that case, again, hydraulic radius of a circular tube would be half r. Now, if I take my permeability and put it in here, permeability of bundle of tube is actually r squared over 8, but if I write it based on hydraulic radius to the power 2, there will be half r here, so factor 4 is already there. I will get 2 denominator here instead of 8. This is my hydraulic radius for the permeability of bundle of tube. Now the main question is, what is the hydraulic radius of this system, of this sand pack system? Hydraulic radius for this sand pack is the pore volume divided by wetted surface. So what's the pore volume that I have here is I need to know how many grains do I have in this system. So the grains that I have here is, let's call it N, which is how many grains do I have? N is if the entire volume was available for the solid to have spherical grains, the volume divided by each grain volume would be the count of all the grains that I have, which is pi d to the power 3 divided by 6. That's 4 over 3 pi r cubic for those who know the volume of a sphere for radius r. For diameter, it would be diameter cubic over 6. But the entire volume is not solid. Only 1 minus porosity fraction of it is solid, because porosity fraction is volume for the pore fluid, for the fluid. 1 minus porosity is the fraction of the solid. Now, this is the number of grains that I have, and so I can get to know what's the surface. What's the surface that will be wetted by this type of butterfly geometry? Is the surface of these grains, right? So that's the S, that is nothing but the surface of the sphere. So the number of grains that I have, each grain has pi diameter square surface, and so they get wet. So hydraulic radius for sand pack of spherical grains will be pore volume. Pore volume is porosity total volume divided by wetted surface. Pore volume is porosity total volume, right? Porosity is the void fraction, is the pore fraction, divided by wetted surface, which is S here. It is N times pi d squared, which is phi v divided by N is 1 minus porosity volume divided by pi d cubic divided by 6. And so if I just cancel everything, what I get is the d comes up, right? I'm sorry, there is also multiplied by pi d2 because this is also here. This comes here. It's N times the surface of each grain. So in total then, my hydraulic radius of the sand pack will be porosity here. D3, D2, two of it will go here and remain one factor. It comes up phi d over, then 6 comes up here, 1 minus porosity. That's the hydraulic radius of sand pack. To write it clean, hydraulic radius will be phi d over 6, 1 minus phi porosity. And now if I put it in the K bundle of tube, it is porosity hydraulic radius square over 2. It will be porosity multiplied by phi d over 6, 1 minus porosity to the power 2 divided by 2. And that means that the grain size d, I can just make it sure that this d is the grain size diameter dp that I have written here. So I put the index p just for simplicity that it is grain size, grain diameter. And the d here also, all of the d's are grain diameters. And that becomes also grain diameter. Doesn't matter, you can keep it d, it doesn't really matter. The permeability using bundle of tube theory will be phi to the power 2 here times phi will be phi to the power 3. Grain size diameter to the power 2 will be grain size diameter to the power 2, phi 3 divided by 6 to the power 2, 36, divided by 2, 72, times 1 minus porosity to the power 2. This is the permeability estimation from bundle of tube theory. Grain size diameter to the power 2, porosity cubic over 72, 1 minus porosity square. This is only found by mathematics and physics. No experiments, nothing. Karman and Kozeni performed sandpack experiments, like what I just showed here. And they found in the lab that the permeability that they found, Karman, Kozeni, they found that the permeability is exactly dp square phi 3 over 1 minus phi 2, but the coefficient here is not 72, it is something like 150. They found it between 150 to 180. Wow! Purely experiment is matching our mathematical and physical model with only a factor of 2.5 times lower in the real experiment compared to the model we have done. What could be the reason for this discrepancy? Why did we overestimate the permeability? Our denominator is 72. The experiment denominator is 150. The reality is that we assume that our tubes are straight, so flow happens straight. But in real rocks that we have in porous systems, flow does not happen like a straight line. It happens very much twisted. we have sudden expansion and contraction in pore geometries, we have twists, change of direction that cause additional friction. So permeability will be seen much smaller in real life than your straight tube assumption that we made in bundle of tube theory. Which means that this is called tortuosity, and tortuosity is the reason that the real practice permeability in the lab is found smaller than the permeability of bundle of tube theory. Was smaller, it was expected bigger than what the permeability from the lab experiment of Karman-Kozeni came. And the reason is that we assumed a straight tubes, while in the lab, reality is that flow is very much twisted. And so tortuosity is the reason behind our laboratory measurements to indicate that the factor 72 needs to be 150 or 180. Nevertheless, this extremely convenient mathematical and physical analysis gives us a great relationship building between permeability, grain size diameter, and porosity for the sandpack system. So if you plot, for example, permeability versus grain size diameter to the power 2, you will find linear relationship, meaning that if grain size is twice big, permeability will be 4 times bigger. If porosity is increased 20%, the relationship is much more complex. It's phi3 over 1 minus phi to the power 2. A coarse grain sample or a fine grain sample, therefore, will have permeability relationship depending on their grain size diameter if their porosity values are the same. This is the basic of understanding permeability from what Darcy did all the way to mathematical analysis and fluid mechanics analysis to obtain a formula that is almost twice as accurate as the real system. What we will do next is now we go towards a more fundamental understanding of what does it mean to have laminar flow as one of the main assumptions that the Darcy flow had. So I said about no slip wall condition, a steady state, fully developed boundary layer, single phase, incompressible, and above all is laminar flow. And if the flow is a bit faster than the pure laminar system, there will be corrections and additions to the Darcy's law due to Forsheimer corrections, which comes in the next lecture. For now, I would like to do a quick recap. Darcy put a sandpack system to understand water filtration system and found that the flow rate is proportional to the potential difference over the length, which is potential gradient or pressure gradient, and the proportionality factor was fluid property driven and rock property driven. And the permeability of the rock was found there, which has unit of a square meter. The values of permeability in real rock systems are very, very small. They are in the order of 10 minus 12. And I will study that. I'll present it to you in the next lecture. And when you do that, you find that also for core flood experiment, you can do this, and then you don't have gravity effect. It's horizontal if you put it horizontal, for example. And if you do one tube analysis, you find that permeability is very much related to the radius of the tube, square over 8, if it is a porous system, phi. And then by definition of hydraulic radius, we can find the permeability for a sandpack, which is at the end almost 2.5 times bigger than what we will find in the real experiments. And the reason is we assume flow is a straight, while in reality, flow in rocks is very much, or porous samples, is very twisted and tortuous. Tortuosity is the reason behind the lab permeability to be smaller than the bundle of tube theory. Next, I'll go to study what's the laminar flow, what does Reynolds number mean, and how can we correct this Darcy law if we have inertial terms also present in my system. Thanks a lot, and I hope it was convenient and comprehensive.